We're going to look at magnets and magnetic fields. We're going to talk about repulsion and attraction. We're going to talk about a permanent magnet, what that means. And then we're going to talk about the Earth's magnetic field that it exists. So first, poles. Poles are just simply the ends of the magnet, the north and south pole. Like the Earth has a north and south pole. They're related, but there's some interesting facts about that to write down. So the first thing I want you to think about. Similarities to electricity. Similarities to electricity. Opposites attract, likes repel. With electricity, positive and negative attracted, but two positives would repel. Same thing here. North and south attract, but two norths would repel, or two souths would repel. Okay, and I mean, honestly, part of me was tempted to bring in magnets and show you this, but I think you've either used magnets before and have seen this before, and it would just kind of be a waste of time. But take two magnets, right? Sometimes they'll pull each other together. Other times you try to put them together, what happens? You can literally feel them pushing apart. When you feel them pushing apart, it means that you're putting the same poles toward each other. So you're taking two north poles and putting them toward each other, they repel. A north pole and a south pole would attract to one another. What's different, though, from electricity is this. You can never get simply a north or a south pole by itself. They always come in pairs. Any magnet has to have a north and a south end. Whereas with electricity, you could have just a positively charged object, or an object that has an abundance of electrons, so it's negatively charged. But for this case here, okay, we're thinking about the fact that magnets have to come with a north and south pole.
The reason why they're attracting and repelling, does it have to do with like the flow of electrons in the field? Like what makes them
Alright, so we're going to get into something called magnetic domain theory this class, which will help explain it. And the idea of magnetic domain theory is the alignment of all the actual molecules in the material. It's a ferromagnetic material, it's got iron in it. And the molecules will realign themselves, all of them, when they're induced with some magnetism. So a magnet itself, all of the poles are aligned. And when you bring a magnet near another one, the top of the pole from this magnet is attracted to the bottom of that. I think it has to do with some sort of weak force or another force, but it's not electrons. It's not electrons that are causing them. I can look more into it. Yeah, but it has to do with the alignment of the poles. When the north and south poles are aligned, they attract one another and they bond together. So when you bring two magnets near each other, they'll pull together because they want to be near one another. Let's see. The names of north and south poles originally came from the way a compass would be oriented on the Earth. And here's what I'm getting at. So draw yourself a quick version of the Earth. So we called one end of the Earth north and one end south. Okay? This was a standard thing to label the Earth with north and south poles. Now, when compasses were starting to be used, the idea of a compass is that one of the ends of the needles is north and one is south. A compass is a magnet that can spin. That's all it is. Okay, just so you know. So here, you have a compass. Draw yourself like a little kite on the compass. Shade the top of the kite. Okay, that's an ugly shading, but I'm trying my best. Okay, shade the upper portion of the kite. Now, the term north end of a magnet came about because one of the ends of a magnet would always face the north pole of the Earth. So, explorers had compasses. They understood the idea that they followed this needle, it directed them north always. Well, the needle that points north was called the north end of the magnet, which is a bit counterintuitive though. Why is that counterintuitive? That this is technically called the north end, and this is called the south end of a magnet. Why is it counterintuitive?
Because that's the part of the compass that points towards which direction you're going.
Okay.
So it's telling you
The compass tells you which direction to go. The dark end of the needle will always point north on a compass. Wherever the dark end is, always goes north. So if you're looking this way, you might be going, let's say, this is north for us. So if you're looking this way, the compass needle went this way, right? The tip of it. Then you start to move and it's going to change. The idea was that whichever end of the magnet always faced the North Pole was called the north end of the magnet. Why is it counterintuitive? It's not wise.
Because actually the south would be facing the north.
Yeah, because why?
They attract.
They attract. So really, here's what's happening. This is called the North Pole, but technically it's called magnetic south. And this is the South Pole, but technically speaking, it must be magnetically north. Think, how could the north end of a compass be attracted to the North Pole? Opposites are supposed to repel, aren't they? So really, what we call the North Pole is really magnetically considered south. And what we call the South Pole is really magnetically considered north. But the etymology of the actual name north and south as poles came from the fact that one tip of the compass, or magnet really, would always face the North Pole. So they called that north because it faced what they called the North Pole. But then when magnetism was more understood, the idea behind it, we think of this really as magnetic south, although it's called the North Pole. Okay? It's really south magnetically, but we call it the North Pole. Josh, question? Okay, let's go to the next. So the second term I want to define is a permanent magnet. And it's a magnet or an object that's made from a material that creates its own magnetic field. So, some materials can be made into permanent magnets. What do those materials usually contain? What is something that becomes magnetic or can be attracted by a magnet usually? Contains what? Okay, specifically, they usually contain X-Men fans? Hello, X-Men fans? No? No one's an X-Men fan? Okay. How does Magneto kill the guard? How does he kill that guard to escape when he's in the plastic jailhouse at one point?
Do you need like a magnetic field or at least something that's metallic?
He creates a magnetic field. He already said metal uses metallicism. But what does he do physically? Tell me. Who remembers the movie? How does he kill him? What does he do?
He just pulls the metal
Out of what?
of his body.
What's in your blood that's metallic? Iron. Thank you. Iron. A ferromagnetic material. Okay, so again, some materials can be made into permanent magnets, and these materials are ferromagnetic. They have iron in them. Now, how do you make something into a magnet that's not a magnet? It's called induction. Remember when we did electricity, we could charge by conduction, polarization, or induction. Anybody remember, what was induction? How did you charge by induction with electricity? Because it relates to this topic. Give you a hint. Charging by contact was called conduction. You would just take a charged particle, touch it to something, you would transfer the charge. That's like when you touch something and you get the static electricity charge. You get that shock. That's conduction. What was induction when we charged objects electrically?
Wasn't it like something with the ground where you had to put it in the ground and then like there was the positive charge, you brought a charge thing to a stable and then the charges went into the ground?
Mm-hmm. And then what did you do with this charge thing afterward?
And then you took it away.
Yeah, you took it away. You removed it. Perfect. So induction is the idea that when you bring another charged particle in the presence of something that was stable in electricity, it caused those charges to separate, you grounded it, and then you removed it. Same thing happens here. So, you bring a very strong magnet in the proximity of a ferromagnetic material, and it will induce magnetism. It will cause the ferromagnetic material to realign the poles inside of it. If held that way for a long enough time, and if the material is what's called a hard magnet, it will stay a magnet. So a hard magnet or a magnetically hard material takes a lot of time and a strong magnet to make it a magnet, but when you remove the magnet away from this material, it will remain a magnet afterward. A soft magnetic material, you could bring a magnet in the presence of it, it will automatically realign its poles. It'll become a magnet right away. but the minute you remove that other magnet near it, it doesn't remain a permanent magnet. So it's like, what's an analogy for this? Oh, an analogy, let me think. Do you remember last year in chemistry, there was a formula Q equals mc delta T? Does that ring a bell somewhere in your brain? mc delta T? Q was heat transfer, M was mass, delta T was the change in temperature. What was C? Remember what C stood for in that formula? Q equals mc delta T. C was measured in, what was it, like joules per kilogram to a degree Kelvin? Kilogram kelvins to a degree there.
Was it calorie?
It was like calories. It was like calories. It wasn't calories, but it was like that. Calories would be used for Q.
Is it heat?
Is it what?
Like heat itself?
Not heat itself. You're both on the right track. It has to do with heat transfer. Let me give you a better example then. Okay, how many people like to cook? Anything? You help your parents cook? Help your mom or dad cook at all? Okay. So, if you've ever cooked with cast iron, you know what cast iron is? If you watch any sort of like medieval times kind of show or anything like that, they used to use cast iron. It's a very heavy iron, but it's durable. If you cook with cast iron, it takes a lot of heat to heat up the pan. A lot. But the pan heats very evenly and will remain hot for a long time period. Now, if you heat up water, it doesn't take much heat to heat up water actually, to heat up water. But it loses heat pretty quickly. That's what C is. Does that ring a bell as to what C is now?
It's like a rating, the rating for like heat transfer. I guess for heat transfer.
Yeah, it's a rating for heat transfer. Good. It's called the specific heat capacity. But a rating for heat transfer is exactly what it is. So here, it's like a rating. So a material that is hard or magnetically hard is like cast iron. It takes a lot to heat up cast iron, but it holds its heat. A magnetically hard material takes a lot to make it into a permanent magnet, but it holds its magnetism after you remove the other magnet. A magnetically soft material can be something like water. It doesn't take much energy to heat it up, but once you remove the heat from the water, what happens? It cools down pretty quickly. Have a cup of tea and it's not that warm out, it'll cool down really quick, especially if it's not insulated, right? That's the idea of a magnetically soft material. If you bring a magnet into the range of a magnetically soft material, it becomes a magnet very easily. But the minute you remove that other magnet, it goes back to the way it was. Okay, it loses its magnetism very easily. All right, third slide. So let's look at magnetic fields. Recall, electric field lines went from one charge to the other. Remember that? What was our rule for electric field lines? Or electric field lines? Or what were some of our rules? Give me anything, because some of them are going to relay on this.
That field lines from positive charge start from the charge and go out, and then lines from for a negative charge start at infinity, go towards the charge.
Yeah, so it always went away from positive and toward negative. Agreed? Does that ring a bell at least? Can you remember it? Away from positive toward negative. What else?
When you had like two positives near each other, the lines didn't even touch.
Yeah, they never intersected. They just showed that repulsion. Same thing here. Bring two north poles near each other, you're going to see the field lines will curl like they did with two positives. What else? There's one other piece of information we used that is useful here. One other piece. The density of the lines. Remember, the lines are closer, makes them stronger. Or the more lines you have, the stronger the field technically is. Okay, so in this case, what you'll recognize, first of all, is the north pole is like your positive terminal. Everything exits the north pole. And where does it go? Which is like the negative terminal. This is just like positive and negative point charges. Now, follow the compass along the field lines. What do you notice? Look at the red arrow. The red arrow points in the direction that the field line is following. So if you ever have a magnetic field and you want to know which way the magnetic field is, you can simply stand there with a compass and you can move. You could follow the North Pole, and as you follow it, you're actually outlining the magnetic field lines. Okay? Let's see. Some other fun facts. 3 things to talk about. 3 more. First, the Earth is not really understood as to why it has a magnetic field. This question, who asked it? Cooper asked in the other class. She said, well, why is the Earth magnetic? Why do we have a North and South Pole? And is it because there's like a lot of iron? Because iron is what causes magnetism. It's not though. Turns out that this is hypothesized, but it's definitely not iron. It's hypothesized that the convective flow of the core of the Earth, like the magma and that fluid, that hot gases and fluids, the plasma that's inside the Earth, its motion is causing the Earth to have a magnetic field. Now, interesting part is that the Earth's poles could switch, and they have switched before. And you feel free to Google this. If you Google like Earth's magnetic poles switching, it happens every I think it's like hundreds or thousands of years. The Earth's poles will switch, and what will happen is because the suspected change of the flow in the Earth's core. Again, this is hypothetical. It's not actually proven yet, but that's the idea behind it. It's not anything to do with the Earth being ferromagnetic. Nothing to do with iron shavings or iron deposits, anything. The hypothesis is the core of the Earth. Second fun fact, most planets' magnetic field strength are directly related to the rotation rate. So if the planet spins on its axis faster, it creates a stronger magnetic field. That directly correlates to the idea of the convective fluids. Because if the Earth is spinning faster, those fluids will be moving faster in the Earth, as a result making it a stronger magnet. Okay, if the Earth's magnetic field is indeed caused by that, section of the Earth's core that is plasma and fluid, and if the Earth spins faster, that core will spin faster, as a result making the magnetic field stronger. Third fun fact is this, and this is interesting. Here's your bio incorporation. Certain bacteria utilize the Earth's north and south poles to direct their own motion. These bacteria, they don't have any sort of way of seeing. They can't actually see physically. So in their bodies, though, they have naturally occurring parts of their body that can sense magnetism. So if they want to move toward the North Pole or toward the south direction, they can actually sense which way they're moving based on the magnetic pull they feel in their body. Okay, so you're using magnetism to relate it to something like, for example, I think one of the examples I gave the other class has to do with like algae coming to the surface. Eventually, algae wants to come to the surface. Why? Why does plant life want to come to the surface?
Because that's how it grows.
Because of what? What causes it to grow?
Sunlight.
The sunlight. So it wants to move toward the top. So it's able to sense a different magnetic pull as it moves. Believe it or not, it's so sensitive that it can tell up and down, left and right, north and south. So it's able to move and navigate without actually seeing. Okay? And I'm guessing that was what? Think back to bio. You think that always occurred? What do you think that was a form of? What do we call that? Evolution. Okay, that most likely, I'm guessing, because of the Earth's magnetic field, these bacteria evolved over time, developing these different parts of their structure that became polarized with the north and south pole so they could sense movement. Okay? A lot of theory. 3 questions for homework. Let's go to the next section. Okay, a little more theoretical. The next section, there isn't any homework. I just asked you to read, I think, a page or 2 in the book.